Hey, welcome back. Today, we're going to crack open a really powerful mathematical idea. It's something that's hiding all around us, in places you'd never expect. We're talking about continued proportion, or as I like to think of it, the unbreakable chain of ratios. So, to get us started, let me just throw a question out there. What on earth could possibly connect the elegant curves you see in geometry, the way your money can grow in finance, and even the beautiful harmonies in your favorite song? And the answer, well, it's actually pretty beautiful. Perfectly balanced ratios. There's a special, kind of elegant mathematical relationship that's acting like a secret blueprint behind all of them. So here's the game plan for this explainer. First, we'll get the hang of the basic idea, what I'm calling the chain of ratios. Then we'll put that to use and start finding the magic middle. After that, we'll level up and tackle some pretty fun proportion puzzles. And to wrap it all up, we'll push the limits and go beyond the basics to see how powerful this concept really is. Okay, section 1, the chain of ratios. Now, I really want you to think of this like an actual physical chain. Imagine the connection between the first and second link is exactly the same as the connection between the second and third. It's this perfect, unbroken flow that makes it so cool. So what does that actually mean, in math terms? Well, it's pretty straightforward. We say that three numbers, we'll just call them A, B, and C, are in continued proportion when the ratio of the first to the second is exactly the same as the ratio of the second to the third. And this slide right here lays it out perfectly for us. A over B equals B over C. Simple, right? Now, A is our first proportional, C is our third, but that guy in the middle, B, he's the star of the show. He's called the mean proportional, and he's basically the bridge that connects the other two. And here's where we get our first little bit of magic. If you do a little bit of algebra on that ratio, literally just cross-multiply the terms, you get this incredibly simple, super useful equation. B squared equals A times C. Seriously, remember this one. This is going to be the golden key we use to unlock everything else. All right, let's jump right into section 2, finding the magic middle. It's time to take that new formula of ours, B squared equals AC, and put it to work finding the missing link in a few of these chains. Okay, first challenge. It's a nice, simple one. Can you find that magic middle number, the mean proportional, that fits perfectly right between 20 and 5? So let's walk through it together. Our middle number, we'll just call it x for now, when you square it, has to equal 20 times 5. Well, 20 times 5 is 100. So we're just looking for the number that when you multiply it by itself, gives you 100. And that, of course, is 10. Oh, and don't forget, it could also be negative 10. See? That wasn't so bad. All right, you're feeling good? Let's kick it up a notch. How about this one? What's the mean proportional between 3x cubed and 27x? Now, I know, it looks a little intimidating with all those variables in there, but I promise you the basic rule we just used doesn't change one bit. And this is just a perfect example of why that formula is so great. All we have to do is multiply the two ends together. So 3 times 27, that's 81. And x cubed times x is x to the fourth. So our middle number squared is 81x to the fourth. Just take the square root of that whole thing, and you've got your answer, plus or minus 9x squared. Same logic, just a little more algebra. Okay, nice work. We've got the basics down cold. So for section 3, let's put on our detective hats and get into solving proportion puzzles. These are problems where the numbers we need are kind of hidden. They're in disguise. So here's our first case. We need to find one single number, let's call it x, and when we subtract that number from 21 and from 15 and from 11, those three new numbers will suddenly click into a perfect continued proportion. So where do we even begin? Well, we go right back to our golden rule. See, the whole trick is just setting up the equation. Our three new numbers are 21 minus x, 15 minus x, and 11 minus x. So we just apply our rule, the middle one squared equals the first one times the third one. Now, yeah, it looks like a mess, I get it, but here's the really cool part. When you multiply it all out, the x squared terms on both sides of the equation just cancel each other out. And what you're left with is a much friendlier equation that you can easily solve to find out that x is 3. How cool is that? That was some great detective work. Now for our final section, we're gonna go beyond the basics. We've totally mastered these little chains of three numbers. But what happens when the chain just keeps on going? And how can we use that idea to prove some really amazing things? And as this shows us, we are definitely not limited to just 3 terms. You can have a chain of 4 or 5 or, heck, 100 numbers, as long as the ratio between any 2 neighbors stays the same. A over B equals B over C equals C over D, and on and on and on. That unbreakable chain just continues.
Now stick with me here, because this next technique is, well, it's an absolute game changer for handling these longer chains. What we do is we just say that common ratio, whatever it is a constant, K. Now this lets us describe every single term in the chain based on the very last one, D. So C is just D times K. That means B is D times K squared, and A must be D times K cubed. Trust me, this little trick is going to let us solve some really tough-looking problems.
Okay, you ready to put that new superpower to the ultimate test? Here it is, our final challenge. Just look at these 2 fractions. I mean, they look completely different, right? But what if I told you that if A, B, C, and D are in continued proportion, these 2 expressions are secretly identical? Let's prove it. So on the left, we've got A plus D over B minus C plus D, and on the right, we've got A minus C over B minus C. I mean, come on the surface, they look like they have nothing to do with each other. But now we have our secret weapon, substitution. This is what happens when we swap out A, B, and C with those DK versions we just figured out. The algebra looks intense, I know, but look closer. In each one of those fractions, you can actually factor a D out of the top and a D out of the bottom. And once those D's cancel out, the whole thing just collapses. That crazy mess on the left simplifies all the way down to just K plus 1. And the one on the right, you guessed it, also simplifies to K plus 1. They were the same all along. And that right there really shows the whole journey we just took. We started with this one simple rule for 3 numbers, and we built on it, step by step, all the way until we could prove that 2 incredibly complicated-looking expressions were secretly the same thing. That's the real power of this idea. So, I'll leave you with this final thought. We started out asking what connects geometry, finance, and music. But now that you know how to spot the underlying pattern, where else might you find these hidden chains? In nature? In art? The pattern is out there, just waiting for you to find it. Thanks for coming on this little math adventure with me.